Hi, I am Michal Wawrzoniak, and I will present Boxer, Data Analytics on Network-Enabled Serverless Platforms. Serverless computing and function-as-a-service platforms such as AWS Lambda or Google Cloud Functions have been rapidly gaining in popularity in the recent years. They are programmed via stateless functions that are triggered on demand. They provide auto-elasticity, on-demand scaling from 0 to thousands of cores and back to 0, and pay-for-use accounting, recently at as low as 1 millisecond granularity. All this while hiding operational complexities, providing easy and fast deployments, and of course, no servers to manage. This collection of features has captured the imagination of many people, and the space of applications that are based on serverless has been increasing dramatically. However, this enthusiasm cannot compensate for shortcomings in the current generation of serverless platforms. As pointed out in CIDR 2019 paper by Joseph Hellerstein and his collaborators, one of the main shortfalls of the existing serverless platforms is the lack of communication infrastructure between functions. In particular, this absence of function-to-function networking makes existing serverless platforms inadequate for all but the most basic data processing applications. This is something that we aim to address in this work. Note that we are currently focusing on AWS Lambda platform. Serverless networking allows outbound connectivity. That is, functions are allowed to initiate network connectivity to external destinations, such as hosts on the internet or other cloud services. However, no inbound connectivity is allowed. Internet hosts and cloud services attempting to initiate network connectivity to functions will be blocked by the NAT gateways that are in front of those functions. And perhaps most significantly, the same mechanism prevents functions from initiating network connectivity with each other. Unfortunately, any non-trivial data analytics or distributed computations require such function-to-function networking. How can that be achieved? Well, looking a bit closer at the restrictions that those NAT gateways enforce, it can be seen that not all is lost. Yes, the NAT gateways will drop any externally initiated network traffic and will only permit network traffic that has been initiated by a function. However, once the connectivity has been initiated by the function, the NAT will also allow the network traffic in the reverse direction to reach back the original function. The connectivity to the outside is bidirectional. And this is how functions can use services such as S3 or other managed services that might be running in EC2, etc. Based on this property, a large amount of effort has been spent to leverage it to provide function-to-function connectivity. In the last few years, a large number of publications have proposed different methods of doing that, including publications by our own group. All of these approaches rely on introducing a data path intermediary that functions can connect to, and then use it to pass data to each other, establishing function-to-function communication channels. There is a variety of proposed solutions and options, such as going through storage services like S3, where functions communicate by reading and writing into agreed storage addresses, or using custom storage or proxy services running in EC2 instances. But all of these solutions have in common is that the intermediary is on the data path. All of the data exchange between functions has to go through those intermediaries. And as a consequence, this results in additional costs in performance, in significant monetary costs, and potentially operational costs. In some scenarios, this reintroduces fixed infrastructure. Is this even serverless at that point? Well, at least it goes against the spirit of serverless. What we really want is no data path intermediaries. We want direct network connectivity between functions, and ideally, just standard TCP. We know how to do this. And Boxer, as I will describe shortly, provides transparent function-to-function TCP networking. The key ingredients are NAT hole punching techniques. These are techniques that traverse NAT gateways. They are commonly used in wide area peer-to-peer systems, since most of the end hosts on the internet do not have dedicated IP addresses and instead are behind NATs, just like serverless functions. Most of these techniques rely on intermediary just to exchange the necessary address information to establish network connectivity. And Boxer uses these techniques to enable function-to-function networking. Boxer runs in the environment of every function. As functions start, they contact an external seed intermediary, for example, running in EC2, and after obtaining required address information, Boxer establishes internal control network, no longer needing the seed intermediary. From this point on, Boxer enables functions to establish direct TCP connections with each other. And in contrast to previous approaches, there is no data path intermediary here. Let's zoom in on a function instance with Boxer to see an overview of the internal network setup process. A function environment will execute at least one function process, as is normal, and it will also execute a Boxer process. The Boxer process primarily provides NAT hole punching services, on one hand to the local function, and on the other hand to remote functions that may want to connect. There is also a compatibility module that is automatically loaded into the function process to provide transparent interface so that the function does not need to be modified. In the scenario where function A wants to establish a TCP connection to a remote function B that is of course separated by a NAT, the compatibility module will intercept the connection request and pass it to the local Boxer service that will then use the already established control network to request of the remote Boxer service of function B to execute the appropriate NAT punching procedure. It then propagates the acknowledgement back to the compatibility module, which then lets the function establish a normal TCP connection to the remote function, which successfully traverses the NAT since it was just configured for it. Notice that Boxer, after the TCP connection has been established, is no longer involved in supporting that TCP connection. At this point, it is just a normal vanilla TCP connection. Measurements of the function-to-function TCP connections reveal that the functions can sustain throughout their lifetime stable throughput of 621 megabits per second. We observe round-trip latency with median of 531 microseconds with a bit higher dispersion. The high-level information bit is that TCP throughput is in the range of achievable S3 throughput, while at the same time, the latency is closer to EC2 latencies. To look at the impact on data analytics, we modified Lambada, a serverless data analytics systems developed in our group. Lambada previously used S3 to implement function-to-function communication. We added TCP functionality and run it with Boxer on a network of 64 instances of AWS Lambda to see effects on TPCH queries. We observe running time speed up of up to 11 times, of course, depending on the query, especially on the number of exchange operators involved. The cost we observe to be reduced by up to 14.9 times. Other than obvious cost saving, the cost reduction also implies that the scope of workloads that are now economically feasible on serverless expands. In summary, we showed an approach and a system implementation to enable serverless function-to-function TCP networking in a real-world function-as-a-service environment. We showed significantly higher performance and lower cost relative to previous approaches. We believe that enabling transparent and direct TCP networking between functions will have broad implications on serverless computing. Boxer is currently in proof of concept early prototype stage with a number of limitations. We plan on improving its reliability, generality, scalability, and usability. We see Boxer as a significant step forward in serverless computing. Thank you.